Well, welcome everyone. Happy New Year, happy 2025. We are happy to welcome you to our first computer vision community session for 2025. My name is Ameed Taylor. I'm one of the co-leads for the computer vision community. I'm also joined by my co-lead Benedict, if you want to introduce yourself, Benedict.
Hello everyone. Nice to meet you again for another new year. I'm the co-lead with Ameed. My name is Benedict. I co-lead the Cohere for AI computer vision group with Ameed, where we do interesting stuff like this, and we invite nice, amazing speakers to come share their research with us. So without any further delays,
Okay, so just before we get started, I like, especially for the new attendees for our calls, to give a quick overview of Cohere for AI. Just a quick overview of Cohere for AI. Cohere for AI is a hybrid research lab and open research community that's dedicated to contributing fundamental research in machine learning. And it works to solve some of the machine learning field's most challenging problems. And probably the most important feature or the most important aim or goal of Cohere for AI is creating more points of entry into machine learning research. So Cohere for AI does that in a number of ways, but I just wanted to highlight a couple before we started our session today. Probably one of the more popular ways that it's done is with the monthly research hangouts. And the research hangouts are an opportunity, for the community to connect with Cohere for AI research staff. It's a way to also get answers to your questions about machine learning research and large language models. It's also a way you can log in or dial in and learn more about working with Cohere for AI's open models and data sets. And you can share research ideas and get feedback. So on our next research hangout session tomorrow, Alejandro will have special guest Marzai. Marzai is one of the machine learning researchers at Cohere for AI, and they'll specifically be talking about multilingual, generative models, and efficiency. So I left a link in the chat for those of you who are interested if you want to join tomorrow. But this is a good way, to get more information in terms of Cohere for AI research, and also questions that you might have in terms of your research journey as well. So again, the next session for Research Hangout will be tomorrow. The other way that Cohere for AI reaches out to the community in terms of increasing our participation in research is via our guest speaker sessions, of course, which we have one today with Nico. But I just wanted to give a quick overview of some of the research sessions that we have coming up for computer vision in the next 4 months. And we'll be adding more sessions as we go on. So we'll have a couple more sessions that we'll announce very shortly. But in February, Alexander from Oxford University and Google will join us to talk about shape image correspondence with no key point supervision. So that'll be a very interesting session. In March, we'll be joined by Mike Walmsley. Mike Walmsley is an astrophysicist at the University of Toronto, and he'll have a very interesting session where he'll be talking about scaling laws for galaxy images. So that'll really be interesting and somewhat different than what we normally have for the computer vision community. So that'll be in the month of March. In April, we'll have a guest speaker from Apple. Madhuri Nagari will join us to talk about texture matching generative adversarial networks. And then finally, in May, we have a session with Samir Atra, and Samir will join us to talk about emotion estimation through facial expressions using computer vision. So we'll be happy to have everyone on the call today join us for these future sessions. And again, we'll be adding more sessions as we go along. So with no further ado, I want to go ahead and introduce our speaker for today. Our speaker for today is Nico Messikommer. Nico is a Ph.D. student in the Robotics Systems and Controls from University of Zurich, and he'll be speaking today about data-driven feature tracking for event cameras with and without frames. We've had quite a bit of interest in this session, especially for feature tracking. So I know both Benedict and I are very excited for this session, and we're excited to introduce Nico. So with that being the case, I'm going to go ahead and segue to you, Nico. Take it away.
Perfect. Thank you very much. Can you see the slides?
They're coming up now. Okay, yes, we can see them, Nico.
Okay, perfect.
Okay.
Well, then thank you again very much for the nice introduction. I'm really grateful to be able to present our work here in this session. I will present our work with the title Data-Driven Feature Tracking for Event Cameras with and Without Frames. This work was done together with Carter Fang, Matthias Gehrig, Giovanni Cioffi, and Professor Davide Scaramuzza. So I will start first by basically presenting a CVPR paper which we published 1.5 years ago, which is the first part. In the second part, I will then also show like some unpublished extension of that work. Furthermore, I will also have some slides, especially at the end of the presentation, to give a little bit other, like an overview of other research in our lab, since our lab is called Robotics and Perception Group. So we also have like some robotics applications. Okay, if you have questions, please feel free to ask them during the talk. I think there will be also a Q&A at the end of it. So whenever you want to ask, just ask the question. Perfect. So let me start by first introducing the goal of our work. I think the slides did just not change.
Yeah, no, okay, it changed.
Okay, perfect. Yeah. So basically, in our work, what we want to do is localize a 3D point in each frame of an image sequence, as visualized here now with the different colored lines. However, the big important thing in our work is that we want to leverage events recorded with an event camera to make this feature tracking more robust and accurate. And furthermore, also to increase actually the prediction frequency of the location of the feature, such that, for example, you also get in between frames actually the location of the feature. So let me first start by explaining why feature tracking is actually important. So one obvious application of feature tracking is object tracking. So you can detect features, for example, on the person. You can track then those features such that you can also then track the person, which is quite crucial, for example, in autonomous driving scenarios where you want to track pedestrians. Another main application of feature tracks is actually more in the robotics domain, where we use the feature tracks to compute the position as well as the orientation of the camera. Here in this slide, you can see like a video of 1 hour of our previous work from our lab. You can see here, like on the top right, actually the feature tracks recorded by a camera looking down, mounted on the drone. By using now those feature tracks, the camera can, or the drone can compute its position in the 3D space. That means it can actually also compensate for external disturbances, which here, as you can see, happens by a person grabbing the drone. A similar concept is also used or was used on the NASA helicopter on Mars. Now you can see here on the bottom right the feature tracks recorded again by a camera looking down onto the surface of Mars. As you can imagine, like the control latency from Earth to Mars is too high. That means that you cannot control the helicopter on Mars in real time from Earth. Therefore, you actually need to have autonomous helicopter flying from given waypoints to another waypoint. In order to do that, you need to find out the position of the helicopter, which was done partially by using also those feature tracks, as visualized here again on the slide. I also want to take this example to showcase the challenges of feature tracking, especially if you consider like normal cameras, like normal standard frame cameras. In future planetary missions, NASA actually plans to explore more craters as well as caves, because they suspect like ice in those caves. And furthermore, they also want to use the caves actually as a shelter for the robot. However, as you can imagine, like in those environments, there are quite challenging illumination conditions, such as high dynamic range, which means there are very bright and very dark spots in the scene at the same time. And of course, there's also like low light conditions inside the cave. Those environments, usually standard cameras suffer quite a lot. And there is like where event cameras actually shine. So event cameras follow a new sensing paradigm based on human vision. Interesting enough, our lab also had some collaboration with JPL to evaluate better like the application of event cameras in space. So let me first introduce like what is actually an event camera. So here on the right, you can see like the output of a standard camera and the output of an event camera. The standard camera outputs at a given frame rate a dense image, meaning that for each pixel inside the sensor, you get an absolute intensity value. In contrast, the event camera output is sparse in space and time. Since event camera trigger like the outputs only based on the changes in intensity, you can see this sparse point cloud. Meaning, like, for example, in this scene, you can see that we look at a rotating disk with a dot on it. And as you can see, actually, the only thing moving or changing is the dot itself. So only at the border of this dot, you get actually some intensity changes. So you also only get events at the border of that. One feature of the event camera is also the high temp resolution, which leads to also this almost continuous like point cloud in space and time. As you can also imagine, the event camera is triggers based on motion. So if there is no motion in the scene, you will also get no events in the output. In contrast, the standard camera will still output like at a fixed frame rate the dense images without considering what happens actually in the scene. Here on this slide, I have also now some names of some companies which produce event cameras. There are also like more, but I've now included like those here. Okay, to now better understand like how event cameras actually work, let's consider one specific pixel on the event camera sensor. Especially, let's consider like the incoming log intensity over time. As you can see here with this plot, there are positive and negative events triggered by an event camera. This depends on if the intensity increases or decreases. Furthermore, like those events are triggered if the intensity change exceeds a predefined threshold, here denoted as C. You can also see here on the bottom of the slide the formula at the point at which a new event is triggered. So you can see the log intensity at the current time step and the log intensity of the time step when of the time step of the last event. Okay, because of those working principle, event cameras have multiple benefits. One of them is high dynamic range, which means they can capture very bright and very dark areas in the scene at the same time. So in this video, you can see here on the left, the event camera image, which can capture the outside and the inside of the tunnel at the same time. In comparison, a standard camera has an oversaturation corresponding to the outside, like the bright outside of the tunnel. Another benefit is like the high temp resolution of the event camera. This enables event camera to capture high-speed scenarios in which normal cameras suffer from motion blur. Another advantage is the low latency. Since the pixel of the event cameras trigger asynchronously and independently of each other, the event camera features a quite low latency. In contrast, a normal camera always just follows the fixed frame rate. So it does not depend what happens in the input. You always get output at this fixed frame rate. However, an event camera, once it detects a change, it directly outputs an event. And finally, as you've seen before, like events are quite sparse in space and time, which means they can be perfectly combined with neuromorphic hardware. And this combination promises a quite significant saving of power consumption, as well as compute. And those advantages we actually wanted to leverage in our work. And those were also leveraged in different applications of event cameras. So before we dive again into the data-driven feature tracking, I first also want to show you like 2 applications investigated in our lab by previous PhD students. The first one is video frame interpolation. Here, the goal is to use a low frame rate video and events recorded at the same time in order to upsample them such that you get a high frame rate video, which means that you get a slow motion video which can capture high speed phenomena, as you can see here, for example, by this exploding bottle. You can see here as well, like we can upsample it almost to 5,000, like more than 5,000 FPS. Another cool benefit of this method using events is actually that you can also record for a longer time these high-speed scenarios. So usually existing high-speed cameras, or in this case, a mobile phone, only can record a small period of time because the buffer gets full quite fast. However, since event cameras only capture like the informative information, so the changes in intensities, they can record for a very long time, basically. So you don't have any problems with a buffer. The second task I also want to quickly present is obstacle avoidance with a drone. Here, like previous researchers from our lab mounted an event camera on a drone and used the low latency to actually guide the drone to avoid obstacles thrown at the drone. So you can see here, there are like multiple things thrown towards the drone, and once it detects it in the event frame, it tries, or like it initiates like avoidance maneuvers. Okay. So let's go back to our work, like data-driven feature tracking for event cameras with and without frames. Again, to recap, what we want to do here is to localize a 3D point in each image of an image sequence using events recorded with an event camera. So let me first start by introducing you how we do this in combination with a normal camera. And I want to start by answering the questions, how can we best track features in the blind time between frames? To answer that, our method first extracts a grayscale patch around a detected feature. In the subsequent events, we then extract an event volume and try to localize this grayscale patch inside this event volume. By finding the correct position of this patch, we actually get the displacement vector of the feature. Here denoted with delta F and also with the green arrow. Importantly here to mention, like this displacement only is between the start and the end of the event volume. So not the start of the frame and the event volume, but actually just in between the event volume. This also means that we accumulate actually displacements of each update such that we get the whole feature track. Okay, to obtain now the displacement, our method first processes both patches with UNet architecture such that we get 2D feature maps. We then use the bottleneck feature of the image encoder together with the 2D features of the events to compute a correlation volume. The motivation here is that we are actually only interested in the center of the grayscale patch. That is why we also only use the bottleneck feature. And that way we also get a 2D correlation map for basically corresponding or correlating the center of the grayscale patch to each pixel in the event volume. The correlation volume and the feature maps are then further processed with recurrent layers to accumulate temporal information. This feature network is then applied for each feature track in one frame. So up to now, each feature track is processed independently of each other. However, to share now information between feature tracks, we introduce a frame attention module. The intuition here is, the intuition is basically that we want to leverage the fact that feature tracks are correlated most of the time in one frame. So let's consider like a static scene and a moving camera. In this scenario, you have quite correlated feature tracks. Now, to share the information between feature tracks, we first leverage the processed feature information together with information from the previous timestamp. And then we use this as an input to a multi-head attention layer. Inside this attention layer, we then share the information between the different feature tracks. Skip connection together with a layer scale is used to stabilize the training, and a simple gating network then outputs the predicted displacement as well as the feature information for the next time step. By now using this frame attention module, we can actually maintain feature tracks in challenging scenarios by conditioning them on feature tracks in the same frame that shared similar motion in the past. So let's assume you have one feature tracks which, for example, changes its texture or gets occluded. However, you know that this feature moved similarly to another feature track in the past. So you can actually take the information of this other feature track to gap these challenging conditions. Okay, so this is more or less the method using the events together with the frame. In the following slides, I want to quickly introduce how we supervise our method. Since there are not many real-world data sets with ground truth optical flow, especially if you also need real-world events, we rely on artificially created dataset called multi-flow dataset. However, since the events are created synthetically, there is a gap between synthetic and real events. So usually, like in simulation, you cannot model the noise behavior as well as the triggering behavior of real event cameras. To now bridge this gap, we introduce a novel fine-tuning strategy based on post-supervision. With this strategy, you can record your own data in the real world and then run a structure from motion algorithm to compute for each image a pose. By then combining the predicted feature location together with the pose, we can actually triangulate a 3D point into the scene again. And then by reprojecting the 3D points to each image frame and computing the difference, we actually get a supervision signal for our tracker. So by leveraging this geometric consistency, we can provide a very or quite robust supervision signal to our tracker without relying on any ground truth feature tracks for real world data. Okay, so let me also show you some results. Here you can see some qualitative video sequences. On the left, you can see the closest state-of-the-art baseline EQLT. In general, what you can observe that our method on the right can track more feature tracks. One thing also to mention here is that we extract the template patch only at the beginning of the sequence and later on just use the events to track. So there is no update of the template, which makes it also quite challenging. Our quantitative results also show that in general, our feature tracks are 2 to 3 times longer than state-of-the-art. Our tracker can also then be applied in challenging scenarios for standard frames, such as in this case, high-speed motion. Here you can see that with a high rotational motion, you can introduce quite quickly motion blur in normal frames. However, due to the high temporal resolution of event cameras, our tracker can still track feature tracks in those high-speed motions. Another challenging condition are low light scenarios, where the standard frames suffer from underexposure. And here we can then leverage the high dynamic range of the event cameras to still track the feature tracks in such low light conditions. Another benefit of our method is actually runtime. So here you can see, like on this slide, you can see two plots for two data sets. So the event camera data set and the EDS data set. On the x-axis, you can see the real-time factor, which means that with a real-time factor of 1, you achieve real-time. And with a real-time factor higher than 1, you cannot run it in real-time anymore. So it's basically the ratio between processing time and the actual considered time period. On the y-axis, you can see the expected feature age, which means like the performance. So what you want to be basically on the top left corner. So you want to be tracking as long as possible and as fast as possible. As you can see here now, like our method performs best in terms of performance. And it also has quite a beneficial runtime. Especially also considering here that this orange triangle on the left plot represents optimized or an ideal implementation of the baseline, which assumes perfect parallelization. One thing to also point out here is in general, like it was a little bit difficult to compare runtime since all of the methods use different frameworks and most of them were also not optimized for runtime. This is especially also the case for our method. So we actually assume that if you spend time optimizing it, you achieve quite easily real-time performance, like real-time runtime. Okay. I also want to show you like another cool thing is, which is basically the combination with standard tracker, like using the Lucas Canada Tomasi tracker for standard images. So what we do here is basically we extract the template patch in the grayscale image. We then use the events and the subsequent time steps to track the feature. And once a new frame arrives, we can actually use this predicted position as an initial guess for the KLT tracker. So since the KLT tracker is an iterative optimization method, that means that the closer you get to the actual position of the feature, the less likely you are to get stuck inside like local minima. This we can also show like quantitatively here by plotting the pixel motion per frame versus the expected age. As you can see here with the red curve, like at the beginning, the combination with between like our tracker and the KLT tracker does not provide that much benefits. However, the more motion you have in the scene, the actually better you get with our combination. So the more accurate or more robust our combination gets. In general, this combination also enables a quite interesting concept where you trigger frames from the frame camera only on demand. So basically only if you have the feeling or if the event-based tracker has the feeling that currently the tracking quality is not good, only at this time point you trigger image again. This has the benefit that you can save computation as well as power consumption, which is quite crucial in AR/VR applications as well as in robotics. Okay, so up to now, what we have considered is the tracker using perfectly aligned event and image data. That means they're like in one sensor plane. Usually this can be achieved by a specialized camera, which captures frames and events in the same sensor plane. Another way to obtain this data is actually to use a beam splitter setup where you have a mirror which splits the incoming light once to the event camera and once to the frame camera. However, what you actually observe in the real world is, or what you observe more is actually a stereo setup where you have an event camera and a normal camera side by side. Especially what we consider here in the following is that you have a rectified stereo setup, which we call here now hybrid stereo. So in order now to track in this setup, like the features, you actually need to find out where the 3D point is observed in the event frame as well as in the normal frame. If you look at this problem statement again, like you actually can see that it is quite similar to the feature tracking. So what you want to do is you want to find a grayscale patch inside an event volume, such that you can actually find the disparity value. So this disparity value means the difference between the 2 pixel location in the event and the frame camera. And the cool thing here is that we can actually use our framework with only minor changes to apply it for this problem setup. So we can reuse again our feature networks to process each feature track independently, and then we can also use the frame attention module to actually share then the disparity information between feature tracks in one frame. To now evaluate this setup, we actually first focused only on the disparity estimation, so predicting the difference between the 2 pixel from the left and the right camera. This disparity estimation we performed then on the M3ED dataset, and you can see here also the table showing the results. We compared against dense baselines, which means that those disparity baselines used all of the frame, like the whole frame, like the whole event frame and the whole image frame. In contrast, in our case, we only use patches. So our method actually has much less information than the baseline. But even though that this is the case, our method still performs quite favorably. You can see that in general, it has a lower mean average error. One thing which strikes out is that if you consider this 1 PE, so basically this one, the error, like the ratio of errors below 1 pixel, you can see that our method performs worse than the baseline. Basically, you can say that basically in the sub-pixel accuracy, our method performs less. However, once you go into larger error, like considering larger errors, we then perform much better than the considered baselines. And we attribute this results actually to the fact that we use or we consider feature tracks along the time as well. Like we use quite a lot temporal information. And by using this temporal information, we can disambiguate better like the disparity at depth inconsistencies. That also leads to this better performance. And as you can also imagine, like since we process sparse patches and not the whole frame, our framework also has a lower runtime than the baselines. Okay, one cool thing you also get with disparities is actually that you can also translate this disparity to depth. So what you can do is actually you can find out the 3D position of the features. And this fact we also used to construct a simple visual odometry pipeline, meaning that we use our framework to compute the camera poses in each time step. And we achieve this by first detecting the features in the camera, like the normal image frame, and then compute the disparities in the event frame. By doing so, we can then find out the depth and then reproject those features into the 3D space. By then tracking the features along the time dimension and by using PNP, we can compute the pose for each camera image. And through this simple visual odometry pipeline, we actually can show that using our feature tracker as well as our disparity estimator, you can achieve already quite well or quite accurate pose estimations, which you can see here now with the predicted tracks and predicted disparity row, which features quite low translation and rotation error. Okay, so let me also quickly present to you how our feature tracker works without considering any standard frames. So up to now, what we have considered is this perfectly aligned images and events, and this hybrid stereo case where you have the frame and the event camera side by side. And in the following, I also quickly want to show you how our tracker works if you only have one event camera. And if you look again at this problem setup using the images, like a normal frame camera, you can see like that what we propose is actually just to replace the image with a grayscale reconstruction computed by events. So there exists other works, like we use now E2VIT, which can convert the event stream again to a grayscale image. And we use these works to actually replace the image camera. And by doing so, we can then show that the event stream actually contains enough information to act as well as a descriptor. So to use it actually for the template patch. You can see here now overall like the quantitative feature tracking results. So you here visualized first are basically our approaches using frames. What you can observe is that especially ours fine-tuned with our post-supervision scheme outperforms all of the existing baselines. And if you now also consider like ours, which uses only events, what you can observe is that, first of all, it outperforms all of the baselines using only events. And it even outperforms on the EDS dataset, the other baselines using frames. Interestingly enough, you can also see that ours using only events performs better than actually the combination between events and frames on the EDS dataset. And we assume that this is the case because there are small misalignments between events and images in the EDS dataset. However, if you use only the events, you get perfectly aligned template patches and the event patch, which then of course helps with the tracking results. Okay, this is our work for the data-driven feature tracking for event cameras with and without frames. If you are interested, we have the code published in the following repository. Up till now, there is only the code for the CVPR 23 paper, so basically only the code for the perfectly aligned event and frame camera. But once our unpublished extension is accepted, we will also upload then the code for this part into the same repository. Okay, since I'm like a member from the Robotics and Perception group, I also want to quickly present actually like another research direction of our group. As I mentioned in the beginning, like our group focuses as well on actually autonomous agile drone flight. You can see here like some previous research works. You can see, for example, on the top left, a drone flying only vision-based through a narrow gap. You can see also some like stabilization mid-air, some drone racing, as well as some drone acrobatics. Especially like in the recent years, our lab focused quite a lot on drone racing. So here you have the task of flying as fast as possible through a sequence of gates, as you can see here, such that you get like a fast runtime. This also led then to a competition between like a human and the AI drone. So basically 2 years ago, we invited the world champions of drone racing to Zurich to fly against our AI drone. And you can see here now in this video, like some snippets of this race. You can see here in blue, actually the AI drone, and what you can observe quite fast is more or less that our drone is always ahead. So you can also imagine that basically in the end we won the race against the humans. One important thing to mention here, like this race was performed only with onboard vision and compute. So there was no communication of an external positioning system or like an external computer. And maybe quickly give you a brief overview, like how it was done. So basically you can see here the onboard view of the drone. it first detects the gates, and based on the gate corners, together with a visual odometry pipeline, they can compute the pose of the drone inside the racetrack. This pose is then used for a reinforcement learning agent to fly through the racetrack in simulation. And crucially, what they show in their Nature paper is that it is quite important to first to fine-tune the simulation with real-world data. So what they have done, they first train in simulation, they fly then this agent in the real world and collect data. This data is then used to fine-tune the simulation, such that in a second training run in simulation, the final agent is then obtained. Okay, that's more or less also like a different perspective or a different research direction of our group. That also concludes my talk. So if you have any questions, please feel free to ask. I'm happy to answer them. Thank you very much for your attention.
Okay, Nico, that was a great presentation. I'll go ahead and kick off. I put a question in the chat. Do you want to read it from the chat, or do you want me to read it off to you?
Maybe you can read it. Okay. Yeah, maybe.
Oh, okay. I'll go ahead and read it.
Yeah.
I was just curious. What are the limitations, or trade-offs of using, the frame attention module in scenes with very dynamic objects, and how, will you guys address that, in future updates or future work?
I mean, that's a really good question. Like, unfortunately, like in our work, we did not test using dynamic objects. So basically, like you have not just a static background, but also like moving objects for the evaluation. But I want to point out that basically we still trained on dynamic objects. So the frame attention module actually learned to handle moving objects. And what we assume what happens is basically that the frame attention module learns to cluster together feature tracks which belong to the same rigid body, so to the same object. And by doing so, like using this attention, you can actually relate feature tracks from one object to feature tracks on the same object. However, as I said, like this, we did not evaluate because like to evaluate it, you need to have ground truth pose. So you cannot use scenes with moving objects. So we did not check this actually quantitatively.
Okay.
Yes.
Let's see. We don't have any other questions in the chat right now. Anyone else with questions? If you want to go ahead and come off mute and ask your question, or you can go ahead and paste it into the chat as well. Hey, Benedict, did you have a question?
No. I will say that the presentation was very expository.
Yeah.
It was very expository. Yeah.
Hey, I got a quick query here. So since you played with the normal cameras and the event cameras, so what do you think about the depth part of it for if evaluating or like matching points with that? Do you need a depth camera too, or like this whole setup will kind of extend there?
You mean like if you have a frame and an event camera side by side, if you need a depth camera to find the correspondences, or?
I was thinking more about like the correspondences as well as like trying to gauge go through the pipeline and experimenting on all the downstream tasks that you have tried. So if we just replace your event camera with a depth camera there, so will the whole process work, or like you will need to take into account the Z dimensions there, the depth dimensions there, sorry, for those pixels or like those tracking points?
I see. So basically, if you replace the event camera with a depth camera, like what happens? Okay, yeah. I mean, it's an interesting idea. I think if you use the depth camera, like one benefit of the event camera is actually that you get fast update rates. Like you get like almost a continuous stream of information. I think if you use in the same way a depth camera, I guess it could make sense. I think the other way around makes more sense. So basically you have a high frame rate video, maybe not as high as the event camera, but let's say you still have like a high frame rate video and you have at the same time a depth camera. Then I think you can still use the same concept to correlate like the feature inside the image and inside the depth image. Such that you can still get like the robustness of depth measurements. I think that could actually work. There, of course, a little bit the question is like how good you can correlate like the images with the depth. But in general, I think that could actually work. Yes.
Yeah. So like I have a depth camera, a RealSense depth camera. So like I was thinking of experimenting and like if the playing around with the pipeline a bit to see how these things work kind of on the downstream task. So yeah, this will be a kind of a good experiment to try on.
Yeah, I think it could be quite interesting. Yes.
Yep. Cool. Thanks.
I had another question. So where can we access the tracks for the EC and EDS data sets, generated based on some of the camera poses that you guys used in your research?
I think I need to double check what we have currently in the repository. I think we only have the code to generate those.
Okay.
But I mean, I can actually also make them open source in the future.
Okay.
Let me double check. But definitely there's code to generate them for yourself. Are you referring for like the supervision or for the evaluation?
More so for the supervision.
I see. Yeah, I think there we only have the code. I think for the evaluation we have the ground truth tracks, but for the supervision we have the code.
Okay.
But I can actually, I mean, you can just also write me a mail if you want to have it earlier. I can share it as well. Yeah.
Oh, okay, sounds good. Okay. I don't see any additional questions in the chat from the attendees who are on the call. Okay, we have a question from Iman Nassef. Iman, do you want to go ahead and take yourself off of mute?
Okay, thank you. Thank you for the presentation and for the session. I know that Davis dataset recordings are HDF5 files, but I want to know how you pre-process the data. I mean, you extract the events from the HDF5 files into another format, or how you use it when you with the network?
Yeah, I mean, to be honest, I don't remember the specific details. Like, I think we used the HDF5, like H5 files to extract it, yes. But there you can find, like, even in our repository, you can find like a data reader, at least as a starting point. And you can also check out like other works from our lab, like RPG. I think there are also other works which use like this H5 format.
But you don't recommend to convert the data into a specific format to work faster, or
to convert it to what? Sorry.
Another format. I mean,
I think internally in our lab we actually found out that H5 provides the best compression and reading speed. So we converged to that format, and we also try to use that in the future. Like we have basically, this is our standard, at least for now, inside the lab. So with H5 you get like quite nice compression, so you don't need to save that much. Like you don't lose memory space that much. Yeah.
Okay, but you are working with the time with the data sparse over time, not you didn't convert it into frame-based.
Yes, we work with the raw event. So basically, really a sequence of XY position,
Yeah.
time step, and polarity. Yeah, we just, I mean, we just use that, and then we convert it then to the format we want, like event representations and so on.
Okay, thank you. I want to ask another question. If you are holding a reading group or anything related to event vision, I can join or something like this.
We don't have one at Cohere for AI at this time. Do you guys maintain a reading group, Nico, for event tracking?
We don't have a reading group, but what you can check out is basically there is this maybe like we have on our GitHub repository from our lab, we have this event-based resources.
Yeah, I know it.
Okay, perfect. There you can find definitely a lot of works. I would also check out like some CVPR workshops, like event-based workshops. They're also quite interesting talks. And also in the coming CVPR 25, there will be again workshops. And though there all the videos are public.
Okay, thank you.
And Nico, is your lab, the Robotics and Perception Group lab, planning to have any presentations at CVPR 2025?
We have some submitted papers.
Okay.
Let's see how it goes.
Yeah, see how it goes, right?
But I think we will definitely also be present in the workshop, like the event camera workshop. Yeah.
Okay, sounds good. Okay, I'll make one more look through the chat to see if we have any other questions. And I don't see any at this time. So thank you again so much for your time, Nico. Benedict, I see you're back. Did you want to close with anything?
Nothing really. I just want to restate again that the presentation was top notch.
Thank you.
I've never heard of event cameras before today, but right now I feel like at the very least I can start doing stuff with event cameras.
Cool, nice. I'm really happy to hear that. Thank you very much.
Yeah. Thank you very much for being with us. We really appreciate that, Nico.
Yeah, thank you very much for giving me the opportunity.
Yeah, thank you for your time. Okay, well, again, we appreciate your time, Nico, and thanks all the attendees for joining. Everyone, please have a great rest of your week. Okay, thank you.
Much.
Bye.
Bye.
Take care, everyone. Bye.